Hello everybody, this is Mr. Tassoni. Today's video will be going over more about quadratic equations and complex numbers, specifically the section on what we call complex numbers. That's section 3.2. So our goals in this video are to define and use the imaginary unit called I. We'll talk about what that is in a minute. We're going to be adding, subtracting, and multiplying complex numbers. We'll also talk about what a complex number is. And then we're going to find the complex solutions and zeros of various quadratic equations. This is very similar to what we do when we solve for regular real number solutions. We're just using a different type of number, which we'll talk about in just a second. All right, so let's go forward with this. So first concept 1A, the imaginary unit I. So not all quadratic equations have what we call real solutions. When we think about the graphs of quadratics, some have two intercepts, like the graph here on the left has an intercept at -1, 0, and 1, 0. So that means it has two real solutions. It could have one intercept, like the graph here in the middle, which has its vertex is the x-intercept right at 0, 0. That's one real solution. Or it could have no intercepts, meaning the whole graph is either above or below the x-axis, and we say that that has no real solutions. Now that's a very important piece of information, talking about real solutions. We're talking about the real numbers here. So to deal with this problem, and by the problem, I mean this third graph that has no real solutions, no x values. Remember in 3.1, we just wrote that it did not exist, DNE. We're going to get a little bit more specific and actually have some values here. So to deal with this problem, mathematicians in the 18th and 19th centuries created an expanded system of numbers using the imaginary unit they called I, and they defined I as the square root of -1. Remember, before we couldn't take a square root of a negative, but now they're saying if I've got a -1, we're going to call that value this weird number I. So just a quick thing on numbers. So this stuff was come up with by Leonard Euler, probably the best mathematician that ever existed. In the 1700s sometime, and then this was expanded on by Carl Gauss, another amazing mathematician, and I think there was one other mathematician that did a lot of work with it, but I can't remember, maybe Bernoulli. My math history is a little bit rusty right now. Anyway, so they came up with this concept of the square root of a negative to come up with answers that were outside of the bounds of what we call the real numbers. So remember, our number system, it's kind of a nested system. You've got natural numbers, which are just the counting numbers from 1, 2, 3, all the way up to infinity. If you expand out from natural numbers and include 0 and the negatives, you get what's called the integers. So again, it's just the positive and negative counting numbers, and then 0, obviously, as well. So those are the first systems that we really learn, and then we move on to a bigger system that includes all of our fractions, decimals that terminate or repeat. We call those rational numbers. So that's just anything that can be expressed in the form of a fraction where both the top and bottom, the numerator and the denominator, are both integers. So -3/5, 10/19, etc. Those are rational numbers. And remember, they terminate or repeat. For instance, 1/3 is 0.3333333 forever if we turn it into a decimal, where 0.5, I'm sorry, 1/2 is 0.5. So those are the rational numbers. And then we have the second group of numbers that's not nested. It's everything that's not rational. Those are the irrational numbers. So the irrational numbers are typically square roots of primes, square root of 2, square root of 3, square root of 5, square root of 17, etc. Special numbers like pi, another number called e, which we'll deal with later on this year. Special numbers like phi, which is the golden ratio, and there's a whole bunch of other weird irrational numbers. So those do not terminate or repeat. So up until now, this is the entire system of numbers that you guys have been using, and we call that group of numbers the real numbers. So all the rationals plus all the irrationals, all the rationals plus all the irrationals make the real numbers. So that's our number system that we use in everyday life. These mathematicians in the 1700s and the 1800s created this new set of numbers, imaginary numbers, which kind of are similar to the relationship between irrational and rational. So imaginary numbers are values like the square root of -1, which equals to I. And we'll talk about other square roots as well. The square root of -25, for instance, is 5i. And there's a whole bunch of different imaginary numbers. And basically, anything that you have in the reals, you could have that multiple of i's that would make our imaginary numbers. So we'll come back to this later on in the chapter, but just know that this imaginary group is separate from the reals. All right, so we've got a property here, the square root of a negative number. So if r is a positive real number, then the square root of negative r is just I times the square root of r. So for instance, the square root of -3 is just going to be I times the square root of 3. And by the first property, it follows that I times the square root of r squared will equal -r. So I'm going to write this out. We've got an example over here, but I want to be very clear with it. So if I've got I times the square root of 5, and I square it, well, that's just the same as saying I times the square root of 5 times I square root of 5. When we multiply roots together, you always multiply the outside portion, the part that's not inside the root, together. So I times I is just going to be I squared, and square root of 5 times itself is going to just equal 5. So I've got I squared times 5. Well, we know that I squared, if I is the square root of -1, then I squared must equal just -1. So I squared is -1 times 5, and then finally I put those back together and I get -5. All right, so let's try some quick problems here. Finding the square roots of negative numbers. So we're finding the square root of the following numbers: -49, -120, and then -8 times the square root of -16. So this is not going to be too bad. We know the square root of 49 is going to be 7, and I've just got a negative sign on it. So what I'm going to do is I'm going to rewrite this. So I'm trying to find the square root of 49, or the square root of -120. Well, the square root of -49 is just going to be 7 for the 49, and then this negative portion, remember a negative sign is just a -1. So this is really -1 times 49 inside my square root. Well, I can take the square root of both of these with the product property. Well, the square root of -1 is equal to I, and the square root of 49 is 7. So I'm going to have I times 7, so times, which is going to equal 7i. So the square root of -49 is just 7 times I. I'm going to remove this so I have some room to work on the next one. All right, so -120, if I take the square root of that, that's going to be a little bit tougher because 120 is not a perfect square. But again, I know I can break this into square root of -1 times the square root of 120. The square root of -1 is just going to be I. I can set that aside. And now dealing with the square root of 120, you guys hear that in the background. My cat is yelling at me right now. The square root of 120, I can just turn that in to a factor tree. I can turn that into a factor tree, and then from there, sorry, I had to get rid of a feline who was trying to get up on the desk while I was recording. Do the factor tree very quickly, and I get the following: 2 times 2 times 2 times 3 times 5. So the square root of 120 is just the square root of 2 to the third times 3 times 5. Well, we know for every perfect square, in other words, every pair of the same number, I can take the square root of that and it becomes a whole value on the outside. So I can pull a single 2 out because I've got 3 on the inside. This pair of 2's, square root of 2 times 2 is just 2. So I'm going to have a 2 on the outside times the square root of 2 times 3 times 5 that's still left on the inside. That's going to be 30. So I've got 2i times the square root of 30. I should bring this down. So I've got an I there times 2 times the square root of 30. I'm just going to rewrite that as 2i times the square root of 30. So there's the square root of 120. It's basically the exact same thing. The square root of positive 120 would just be 2 times the square root of 30, or 2 radical 30. Since I've got that negative sign, I'm just going to factor out an I, or take the square root of the negative 1 and make an I out of that. And now I've got 2i times the square root of 30. All right, last one. This one's a little bit tricky, but not too bad. Negative 8 times the square root of negative 16. Well, this negative 8 is already taken care of. I'm going to leave it outside for a while, and I'm just going to deal with the square root of negative 16. Well, I know the square root of negative 16 is just going to be the square root of negative 1 times the square root of 16. And the square root of negative 1 becomes the letter I, the imaginary number I. And square root of 16 becomes 4. I bring down my negative 8 now, and I got negative 8 times I times 4. Put it all together, multiply all this together, and we get negative 32i. So whenever you take a square root of a negative, you're going to get an I out. That's the big takeaway here. All right, let's continue along. So complex numbers. This is the definition of complex numbers. So a complex number is any number written in the form a plus bi, composed of 2 components. We've got a real number in the form of a, so just any real number, whatever it is, and an imaginary number in the form b times I. So examples here are, we've got our real parts 4, that's the only real part in these, and then we have the imaginary parts, 7i, negative 3i, 18i, etc. So going back really quick, we go back to this diagram over here. That means if we combine the real and the imaginary groups into just one big system, we call that the complex numbers. And examples of the complex numbers would be 3 plus 5i, negative pi minus 7i. Technically, the number 5 would be a complex number. It just has 0i. Same with negative 5i. That's a complex number, even though it has no real part. It's technically 0 minus 5i. So complex numbers pulls the reals and the imaginaries together to make a new type of number. You might be asking, like, what is the use of this? Well, what's interesting with mathematics is that this was purely theoretical and didn't really have a lot of application when Euler and Gauss and Bernoulli worked on it in the 17 and 1800s. But when we moved into the industrial age and people started making things that ran with electricity, electrical engineers and physicists found that the complex numbers were very useful in calculating various things with voltage and impedance and all this interesting stuff with electricity that I don't know a lot about. That's more in the realm of physics, but it plays into electricity and magnetism and all the complex equations that they're doing with that. So the way math works sometimes is that mathematicians build new mathematics that are very kind of crazy and weird and out there and don't really have any applied value. And then maybe decades or even centuries later, new technology suddenly, it's realized that that new technology can use this. So if any of you are interested in going into like electrical engineering or wanting to become physicists, you'll deal a lot with complex numbers, especially in the classes that you're taking as you're working on your degree. Luckily, as a mathematician, I only had to take basic physics. I didn't have to mess with electricity too much. So this is a little bit beyond my scope as far as that goes, but that's kind of the reality of math as it's invented. All right, so back to complex numbers. So two complex numbers, a plus bi and c plus di, they are equal if the a value is equal to the c value and the b value is equal to the d value. So also note, all real numbers are technically complex numbers. They just have 0i for the bi component. Just like all imaginary numbers are also technically complex numbers, they just have a 0 for the real component. So you can really think that all numbers are complex numbers. All right, so our next goal is just solving for the equality of two complex numbers. This is just this algebra that we're doing here. We're finding the values of x and y that satisfy the equation 3x plus minus 8i equals 12 plus yi. Well, to solve this, if these are equal, that means that the real component is going to be equal to the other real component. So I can solve that. Find that x is equal to 4. And also the imaginary component, negative 8i, is going to equal the other imaginary component. Well, we can divide both sides by I. This is not very magical. And we have that negative 8 equals y. And we've solved it. Equality with complex numbers is pretty simple. At most, you're going to have to do single-step equation with algebra. And in both cases, I just divided. On the left side, I divided by 3. I'm hoping that you understand what I did there. If not, please contact me. All right, so concept 2, this is getting into more interesting stuff. Operations with complex numbers. So all complex numbers can be added, subtracted, and multiplied very similarly to real numbers. To add or subtract complex numbers, all you have to do is add or subtract the real parts and then do the same with the complex parts separately. We've got a little diagram from the book here. I've got a plus bi plus c plus di, then I'm just going to add a plus c together. And then finally, I'm going to add bi and di together. Same with the difference. You just do the subtraction piece by piece. A minus c gives me a minus c, and bi minus di gives me b minus d times I. Or you could just have bi minus di. Multiplying, because all complex numbers are expressed as a binomial, you're going to either be using the distributive property or the FOIL method to multiply. And we'll talk about those in a slide or two. All right, so let's do some addition and subtraction with complex numbers. This is very fast once you get the hang of it. And you're just writing the answer in the standard form for complex numbers, which remember is a plus b I. So I've got 23 minus I plus 45 plus 2I. So I'm adding 23 plus 45 is going to equal 68. And then negative I plus 2I. If I've got negative I, that's negative 1I. I'm adding 2I to that, so it's going to take me to positive I, or positive 1I. There's my answer. Like I said, this is very fast. 3 minus 7I minus 2 minus 7I. Well, 3 minus 2 is just going to be 1. And then this is just a little tricky with the signs. I've got a negative 7I, and I'm subtracting another negative 7. Remember, if I'm subtracting a negative, that's going to become a plus plus. Negative 7I plus 7I is going to be plus 0I at the end. If it's 1 plus 0I, you don't really need to write the 0I, so it's just going to be 1. All right, and let's do the last one now. 18 minus 3 plus 6I plus 2I. Well, the negative sign applies to both values inside the parentheses. So 18 minus 3 is going to equal 15. And then I've got a negative 6I plus 2I more, which is going to take me back up to, oops, not plus. Negative 6 plus 2 is going to bring me up to negative 4I. That's adding and subtracting with complex numbers. You can kind of almost think of the I value like you would a variable. I've got 3x plus 4y minus 2x plus 7y. Well, 3x minus 2x is going to be x. 4y minus 7y is going to be negative 3y. You process it the same way. But just remember, I is not a variable. I is a number. It's just an imaginary number. We give it that value, I, to make sure people know that we're talking about imaginary numbers. All right, next up, multiplying. Same principles hold here. It's still not bad. We're either going to distribute like in the first one, or we're going to use the FOIL method. This first one, I'm just distributing 3i into the parentheses. So 3i times negative 5 gives me negative 15i. That's easy. And then the second part is going to be 3i times 2i. Well, that's going to give me plus 6. 3 times 2 is 6. I times I, though, is going to give me I squared. Be careful about I squared. Remember, I is equal to the square root of negative 1, which means that I squared is equal to negative 1. So this is going to be negative 15i plus 6 times negative 1. I can then multiply the 6 and negative 1 together. That becomes minus 6. So I've got negative 15i minus 6. I want to get this in standard form, so I'm going to put the real part out front. Negative 6 minus 15i. All right, next one is going to require the FOIL method. Still not too bad, though. First, 10 times negative 2 is going to be negative 20. Outer, 10 times 3i is going to give me 30i. Inner, negative 7i times negative 2 is going to give me, well, a negative times a negative is a positive. 7 times 2, 14, and then I. And then last, this is the only tough one, negative 7i times positive 3i. Well, negative times a positive is a negative. 7 times 3 is 21. I times I is I squared. Well, remember that I squared is going to become a negative 1. So negative 21 times negative 1 is going to turn it into a positive 21. The middle part, we've got some i's that we can combine like terms with. 30i plus 14i gives me 44i. And then I've got the negative 20 at the front. Oh, let's fix that. That's a mess. Negative 20 out front. Oh, don't forget the plus sign. So I've got negative 20 plus 44i plus 21. Well, again, I've got some like terms I can put together. I've got negative 20 and positive 21. So what I end up with is positive 1 plus 44i. Now I've multiplied those complex numbers together. All right, so that's all the operations. Next up is the last goal or last concept. It's finding complex solutions of quadratics. So remember at the very beginning of the section, we talked about how we have these situations like in the graph here where I don't have any x-intercepts. I've got nothing along the x-axis. Well, instead of saying that we have no real solutions, now we're going to say that we actually have two complex solutions. Because all quadratics, remember, quadratics are x squared in the function. So if there's x squared, there should be two x's, either two real solutions, one real solution that is actually what we call a double root. Technically, both factors or both x-intercepts are at the same location. That's when we have one real solution. Or we've gotten two complex solutions where the entire quadratic is above or below the x-axis. All right, so we can use these quadratics, we can solve these quadratics where we previously would have gotten no answer, and we have these two complex solutions. So let's go ahead and solve. Complex solutions of quadratics. This is not going to be tough at all. We're going to use the same principles we've done before. I've got x squared plus 9. Well, if I've got x squared plus 9, I can either think of it, well, I'm not going to use the Xbox method because that's going to actually make it kind of tough to visualize. But if I've got x squared plus 9, just set it equal to 0. Subtract 9 on both sides. I get x squared equals -9. We're almost done already. Take the square root on both sides. I'm going to end up with x on the left. Square root of -9, that's going to give me 3i. And remember, this is an x we're solving for, so we're still going to have the plus or minus 3i. So our answers really are x equals positive 3i and x equals -3i. You want to see how that works, we can plug those back into the equation. I'm gonna set this, let me take a screenshot of the second equation. We'll do that in the black area. So if I have x equals 3i and x equals -3i, you can technically say that we've got an intercept form, x minus 3i and x plus 3i. If I use the FOIL method to put this all back together, x squared, x times 3i, that's going to be plus 3xi. Then the inner values, it's going to be -3xi. And finally, the outer values, -3 times positive 3i. So negative and times a positive is negative. 3 times 3, 9. I times I squared. Well, we know that these are the positive and negative of each other, so these middle values are going to cancel out. The x squared is going to stay the same, and then the -9i squared is going to become -9 times -1, which becomes +9. I'm going to bring over my x squared from the left, and I get x squared plus 9. So this has two complex roots, positive 3i and -3i. All right, let's go ahead and try the last one. I should paste in, I hope. All right. Let's lock that. So this one's a little bit tougher. I've got 2x squared minus 25 equals -71. Well, all I have to do is solve this just like I would any other algebraic expression. 2x squared minus 25 equals -71. I'm going to add 25 to both sides. So I end up with 2x squared equals, what do I got here? Negative 40, what, 46? That makes sense. Yeah, 2x squared equals negative 46. So now I just have to divide by 2 on both sides. I'm left with x squared equals negative 23. Well, 23 I can't break down at all, but I can take the square root on both sides. If I do that, the square root of x squared becomes x. I'm going to end up with plus or minus square root of negative 23. Well, the negative 23, remember, is just the same as negative 1 times 23. So square root of negative 1 is going to become the I, and the square root of 23 is just going to stay square root of 23 because it's a prime number. So I get plus or minus I times the square root of 23. And those are my two complex solutions, or two complex roots, or two complex intercepts, because they're not really intercepting anything that's real. All right, last one. Find the zeros, which is another word for solution or roots. Remember, the zeros are just the value that when I plug in x, I'm going to get a 0 out for my output. So basically, all I'm doing is solving an equation that looks like this. 0 equals 7x squared plus 91. Well, again, that's pretty easy. Subtract 91 on both sides of the equation. I get negative 91 equals 7x squared. We're almost done already. Divide by 7 on both sides. Negative 91 divided by 7 is going to equal negative 13, which equals x squared. So again, all I have to do is take the square root on both sides. Square root of x squared gives you x. Square root of negative 13, I'm going to have a plus or minus I times the square root of 13. Super fast. And that is our section on complex numbers. The biggest takeaway in this is just learning how to take these complex roots. And really all you're doing is doing the exact same thing as you would with a square root, except you're going to have a letter I in there if it's negative. Once you get the hang of that, the rest is relatively easy. All right, so this is the video. I hope that it was informative. We'll be talking about this in the next class section. There will also be an assignment for 3.2 assigned when I launch this video to you guys. Have a good day, and let me know if you have any questions or issues. Thanks.